This is lesson 14 on programmable logic devices. PLD stands for programmable logic device. CPLD stands for complex programmable logic device. Now we saw in lesson 13 that TTL circuits were developed that contain AND gates, OR gates, NANDs, and a variety of other relatively simple logic functions. But each TTL chip just did a single function. Well, as you could pack more and more transistors in a single chip, the question arose, could you make a single chip that you could program to do any one of these functions? Well, this led to this basic PLD structure. This sort of looks like the circuit diagram that we drew when we did the sum of products for the exclusive OR gate, you remember. You get two inputs X and Y with inverters, so everything along here is X, here's not X, here's Y, this is not Y. And here are two 4-input AND gates, and here's a 2-input OR gate. So this implements sort of a sum of products. Z is A or B, where A is whatever these AND operations are. And the idea is, think of removable jumpers here where you can connect any of these, and let's see what happens if we connect them all together here. Then this input would be X and not X and Y and not Y. Well, X and not X, you remember, is 0, and Y and not Y is 0, and 0 and 0 is 0. So if we connect all of these together, we get 0 here. But if we opened any of them up, we could get something other than 0. So in this case, Z, which is just A or B, would be 0 or B or just B. So whatever we connected here would be what Z became as long as we closed all of those switches. Well, let's see how we can make an AND gate out of this. Suppose we just connected these two. We close all these, so B is 0, so Z is going to be whatever A is, but A is just X and Y. Now when I don't connect anything, what happens is this input floats high, so it's considered to be a 1, so we AND that with 1, ANDed with 1, which means we just get, in this case, X and Y. So here's how we can implement an AND gate by starting with this basic structure and just closing those two switches. If we wanted an OR gate, we just change the switches. So if we connect this one to X, A would be X, connect this one to Y, this B would be Y, and Z is just then X or Y. Okay, see if you can figure out what kind of gate this is. If you close all these, what's B? 0. But now I connect this to not X and not Y. So A, and therefore Z, is going to be not X and not Y. What's that? Well, not X and not Y, we can apply De Morgan's theorem and get not X or Y, which is what kind of gate? A NOR gate. What type of gate is this? What's A? A is not X. B is not Y. So Z is not X or not Y. Apply De Morgan's theorem again. Not X and Y. What kind of gate? A NAND gate. Okay, now here's an alternate representation. We just showed an AND gate that had 4 inputs. But in general, in a PLD, you could have many more, such as 32 inputs here, so it becomes impractical to draw all of the lines. So instead we draw a single line, and we indicate an X here if it's connected here. But this single line isn't really a single line. In this case, it's really 4 lines collapsed into this single one. And this is really 4 lines collapsed into a single one. So this is just like closing all of the switches, so this output A would be 0, and it's just like closing all of the switches here. So to program it, we just open up one of these gates. This is how it's actually done. If you erased one of these PLDs, you'd close all these switches. When you program it, you'd open selective ones. So to make an AND gate, we would then just end up opening these, so these would end up connected. So A is really X and Y, and B is 0 in this case, so Z is just X and Y. Okay, here's a schematic for a specific PLD called a GAL16V8. It has 16 inputs altogether here that can be inputs. These pins 2 to 9 here can only be inputs. These I/O ones, 12 to 19, can be either inputs or outputs. Of course, at least one of them has to be an output if you want to get anything out of this chip. And this GAL16V8 has this basic structure. It looks similar to what we had before, except now we have 8 of these AND gates, each with 32 inputs. I've only shown 8 in this picture, but there are really 32 coming in here. And then a great big 8 input OR gate. So this output pin 19, depending upon how you program this, could be any function. I've shown 2 inputs here, X and Y, coming in. This little symbol here is actually an input buffer that has both no bubble and bubble. That is, you put X in, you get both X and not X out. And so this line is X here. This line is not X. This would be Y here. This is not Y. The ones I skipped here actually get connected to the outputs of some of these other output pins. They get wrapped around. So you can program this to be almost anything that would fit in this chip. Now, those are examples of PLDs. As you could put more and more transistors into a chip, then CPLDs, or complex PLDs, were developed, which is basically lots of PLDs inside a single chip. Here's the Xilinx 9500 series, a bunch of I/O blocks, some switches to move them around, and output function blocks. Here's the 9500 family. Here's different ones. The 95108, for example, has about 2400 usable gates. Now, the 95108 has 6 function blocks. Each one of those contains 18 macro cells. We'll see what's in there in a minute. Each macro cell behaves like a GAL32V8. That is, it has 32 inputs and 18 outputs. And it's an AND/OR array for the sum of products with 32 inputs and 18 outputs. And it behaves similar to those GAL chips I showed you before. Here's the architecture again. These are the inputs, and they go to these 6 different function blocks. And inside each of these function blocks is a macro cell. And the macro cell is, again, a bunch of AND gates. These come out. You can picture these connected to any of the inputs, just like we had before. Here's the output OR gate, so you can OR any of the outputs of these AND gates. Here's an exclusive OR gate. You'll notice this is a little multiplexer. We'll talk about multiplexers in future lessons. But this becomes a controlled inverter. You remember how exclusive OR gates can be a controlled inverter, so you can either invert the output or not. This little block happens to be a flip-flop. We'll talk about flip-flops in later lessons as well. So this is the macro cell for the 9500 series of CPLDs. Now, CPLDs, you could basically implement this sum of products. But in the next lesson, we're going to look at a different kind of programmable logic device called an FPGA, which is what we actually use on our Nexus 2 and Basis boards. And that uses a completely different architecture than those used in these CPLDs.